Hi guys, today we will continue our week 11 topic 4 soil compaction and consolidation. This topic will cover in week 11 to week 14. Program outcomes PO1 and also PO2. And we have course outcomes, CO1 and also CO2, and also we have CO-PO mapping, CO1, PO1, CO2 and PO2. Learning outcomes. At the end of the lecture, students should be able to understand the theory of compaction, dry density, moisture content relationship. Number 2, understand the laboratory compaction test using standard and modified Proctor. And number 3, determination of maximum dry density and optimum moisture content, airward curve from compaction test using standard and modified Proctor test. Now we go for the first subtopic, which is compaction. Firstly, we go for the introduction. Compaction is a process that brings about increase in soil density accompanied by decrease in air volume or air content. It is a process of packing soil particles closer together by mechanical means, for example, rolling, tamping, or vibrating. The degree of compaction is measured by magnitude of dry density achieved, and it depends on the water content and the applied compactive effort, such as weight of framer, number of impact, weight of roller, and number of passes. For a given compactive effort, the maximum dry unit density occurs at an optimum water content. Alright, you will see the figure here. This is the initial or original soil. Alright, and then after that, we do the compaction and apply the compactive effort, and it will expel the air. And then you will see here the volume is reduced. Now we go for the application of compaction. Soil used as fill. It will use to refill an excavation or void to provide made-up ground to support a structure as a subbase for road, railway, or airfield runway. And number 4, as a structure such as earth dam. Okay, when we use as the fill, so this is the application. So how about the improvement by compaction? When we do the compaction, we will improve some of the properties. First is we will have the higher stability of soil, higher CBR value, lower compressibility of soil, lower permeability, lower frost susceptibility. And how about the effect on mass of fill? We will have the greater stability, less settlement, less deformation, less water absorption, less risk of frost heave. Alright. Look at the result of poor compaction. Right, you will see here, this is first one. You will see the basement and pool crack and leaks. Right, you see here, leakage, and leaking happen. Alright, so this is another example. Slab cracks. Okay, when we have the poor compaction, there will be a settlement and the slab cracks. And you will see here pipe leakage and breaks. And then we will see here is the foundation erosion. If you see here, under abutment also have the settlement and failure. And this one is the utility trench. Right, see? there may be a failure there, right? Now we go for the objective of compaction. There are three objectives. First is to increase the shear strength and bearing capacity of soil, right? Number two, to increase the stiffness and therefore reduce future settlement. And number three, decrease the void ratio and also reduce the permeability value. Alright, so now we go for the factors affecting compaction. First is nature and type of soil. Different type of soil will give you the different result of compaction. Okay, for example, if you have a sand and also clay. Okay, for the sand, you know that we will classify the sand as the well-graded or poorly graded or uniformly graded. Okay, so for the clay plasticity, we will see the high plasticity, low plasticity, and so on. So for different type of soil, the compaction will be different. Sand will have the better compaction compared to the clay. And then number two is water content at the time of compaction. Right. Number three, site condition. It depends on the weather, type of site, and layer of thickness. Alright. And then the type of compaction plant being used. Okay, it depends on the weight, vibration, and number of passes. Okay, when you increase the number of passes, the compaction will be better. Okay, and then maximum possible state of compaction attainable for the soil. Alright, and the last one is maximum amount of compaction attainable under field condition. Okay, with different amount of compaction will give you the different compaction value, right? Alright, now we go one by one. First is effect of type of soil. Okay, well-graded granular soil can be compacted to higher density than uniform or silty soil. Okay, clay of high plasticity may have water content over 30% and achieve similar densities to those the lower plasticity with water content below 20%. Right? So meaning that here, if we see that coarse type of soil will have the higher densities compared to the fine type of soil. Alright guys, look at this. This is the effect of soil types. Effect of soil type to the compaction. Alright, so y-axis is row dry. This is dry density, and x-axis is moisture content, the percentage of moisture content. And we see here we have different type of soil, and you have the first one is silty or fine sand, and you have the clay high plasticity, clay with low plasticity, and sandy clay. If you see here, all of these type of soil, we have the lower value of dry density compared to well-graded sand. For well-graded sand, we have the higher dry density. Okay, so means that if you have different type of soil, it will give you different value of dry density. Okay, maximum dry density. If you see, we have the maximum dry density. We have the greater maximum dry density for well-graded compared to the poorly graded, and will be high dry density for coarse soil compared to the fine soil. Now we go for the effect of compactive effort. Okay, the compactive effort will be greater when using either heavy roller on site or heavy rammer in the laboratory. With the greater compactive effort, the maximum dry density will be increased. The optimum water content will be decreased. Okay, remember this one. The MDD increased, the OWC will be decreased. And then air content remains almost the same. Alright guys, look at this. We look at the effect of compactive effort. Alright, so as usual, this one is dry density, and we have the moisture content, and then you compare with different compactive effort. Okay, we're using 2.5 kg rammer and also 4.5 kg rammer. If you see, for the 4.5 kg Rama, the dry density is higher compared to 2.5 kg Rama, because the higher competitive effort will give you the higher value of dry density, and it will reduce the optimum water content. Now we'll look at the relationship of dry density and water content. As you know that for compaction, we have to draw the dry density versus water content. Y-axis is dry density, x-axis is water content. So what we do is we will plot the dry density of soil versus water content. So for example, here we have 1, 2, 3, 4, 5, 6 points, for example. And then what we do is we get the value of maximum dry density. For example, here is this is the maximum value, and then you will have the maximum dry density here, and then at the bottom you will have the optimum water content. This is the relationship between dry density and water content. We will get the maximum dry density and also optimum water content. Alright, now we look at the relationship of dry density and air void content. Curve for different air content can be added to the rho D over W. Rho dry over W, plot using this expression. So you have to remember this equation. Rho dry is equal to GS times rho water over 1 plus water times GS times 1 minus AV. AV is air void, GS is the specific gravity, W is moisture content, the percentage of water content or percentage of moisture content. Rho water is density of water, and GS is the specific gravity. So you have to calculate the rho dry, right? The air void content corresponding to the maximum dry density and optimum water content can be read off the rho dry over water plot or calculated from this expression. Alright guys, for air void content, we may have at 0%, 5% or 10%. Okay, after you draw the rho dry versus moisture content, okay, and then you will get this blue curve, and then sometimes you have to calculate the value of air void content. You have to plot the air void content, air void curve. Okay, so for 0%, 5% and 10%. All right, so if you notice here, for the 0%, the air void curve, okay, this one is actually curve, it's not a straight line. The air void curve should be outside from the blue curve, right? This is the rules that you have to follow. It must be outside from the your density versus water content curve, right? The compaction curve. Okay, if your air void curve 0% is inside the your blue curve, so means that there is something wrong with your calculation or your test. Now we go for the laboratory compaction test. Types of compaction tests, we have standard proto test, okay, using 2.5 kg Rama, and then we have the modified proto test, we have 4.5 kg Rama, and the last one we have the vibrating Rama test. Alright, now we go for the standard proto test. This test is used for the soil finer than 20 mm. Okay, the soil sample, look at the soil sample, the mass required is about 5 kg. The size soil must be less than 20 mm. The procedure, you are using number of layer 3 and number of blows 27 number of blows per layer. Alright, and then you look at the Rama. Okay, this is compactive effort. We have the mass of Rama 2.5 kg, face diameter 50 mm, the height drop of Rama about 300 mm or 0.3 meter. Okay, the volume of mole is about plus minus 1000 ml. The internal diameter is about 105 mm. Internal height is about 115.5 mm. It is plus minus 1000 ml. Right? Alright, this one is standard proto test for soil larger than 20 mm. The soil sample mass required is 25 kg. Size limit mostly less than 37.5 mm. Alright, the procedure, we're using the number of layer of 3, number of blows, 62 per layer. Alright, and the rammer is 2.5 kg, face diameter is 50 mm, height of drop is 300 mm, using a CBR mold, volume 2300 ml, internal diameter 152 mm, and internal height 127 mm. This is for soil larger than 20 mm, but less than 37.5 mm. Alright, other than standard proto, we have the modified proto test. It attempts to more accurately reflect the heavier compactive effort available on site. The heavy BS compaction test is basically the same as the pretty standard test, but using 4.5 kg with falling 450 mm instead of 2.5 kg falling 300 mm. Alright guys, look at this. This is compaction test procedure. You may look at the test procedure in this YouTube link or YouTube channel. Alright, so this is the standard proton mold. We have the collar mold and the base plate. Alright, this is the basic apparatus. So what we do first, procedure is first you have to clean the mold and the base plate. Alright, and then second, feed them and record the weight. So you have to record the weight of mold and also the base plate. Alright, the first procedure is first you have to take about 5 kg of air dried sample passing on 37.5 or 20 mm and sieve the soil, and then you have to add adequate water, mix the soil with the water. Okay, you have to repeat the same procedure for 5 or 6 times. So first water, maybe you take about 5% of water, and then a second test maybe you will take about 10%, and third test you take 15 and 20 and 25% of water. Okay, so this one and then what you do is you mix the soil with the water, right? Okay, next step is you attach the collar to the mold, fill the soil into the mold. Okay, this is the mold. Then you have to attach the mold and then you fill the soil into the mold. And then after that, you compact the layer in the mold in 3 equal layers using rammer at 27 blows per layer. And then after that, you have to remove the collar. After you compact, you have to remove the collar and cut the excess soil with a straight edge. Clean the mold from the outside and record the new weight, the mold, and also the soil, right? And then what you do is you have to take out the sample from the mold using sample extruder. Okay, keep a representative soil specimen for water content determination. Alright, so means that from this sample, you will take about 3 small sample to get the value of moisture content or water content. Alright, so you have to repeat the test about 5 to 6 times with gradual increment water content, each time by adding a sufficient amount of water in the soil. So means that, for example, for soil you take about 5% water and then you take another 10. Alright, so 5 to 10 to 15 to 20, 25 to 30% of water. Alright, so first step for calculating, for calculation for compaction. So first step is calculating bulk density. So first step, just now we have the mass of mold. Okay, the mass of mold is mass of body and base. And then the last step, just now we have the mass of mold plus mass of compacted soil. So from this, we will get the M3, which is mass of compacted soil. Okay, M2 minus M1. So actually what we do is we have to determine the value of bulk density. Roll bulk is equal to mass over volume. Mass of soil over volume. Volume of mole. Alright, so you will get the value of roll bulk in mg per meter cube or gram per centimeter cube. And now we have to calculating dry density. To calculate the dry density, roll dry is equal to roll bulk over 1 plus W in percentage. Remember W in percentage. For example, your W is in 20%, so you have to put here as 0.2. Alright, so you will get the value of dry density. This one is already covered in chapter 1. Okay. Alright, now guys, this is an example. In a typical compaction test, the following data might have been collected. First is we have the mass of mole, we have the volume of mole, and the specific gravity of soil grain. Alright, so first is you have to determine the value of bulk density. Okay, we have the mass of mole and soil, and then we have the value of water content. Okay, water content. So first is you have to remember that we have to determine the bulk density. Bulk density is equal to m over volume. M is mass of soil, and then we have the V, volume here. All right. So first is mass of soil. So we have to minus with mass of mole. For example, here 2833 minus 1082. Alright, and then we will look at the next slide. Alright, so to determine the bulk density, so you have to use the m minus m naught, meaning that m with mole and soil minus mass of mole. You will get the mass of soil, and then the volume of mole. Right, so first is we determine the bulk density. Okay, rho is equal to m over v, mass of soil over volume. So this is the value. Okay, and then you have to determine the water content. The water content here. Alright, and then dry density. Dry density is equal to rho bulk over 1 plus W. W is the water content here. So this is the dry density. Why we determine the dry density is because we are going to use the dry density versus water content. Okay, alright. Alright, now determine the maximum dry density and optimal water content. So first is you have to plot the density versus moisture content. Okay, from the previous slide, you will get the first point, second point, third, fourth, fifth, and number 6. Okay, we have 6 points, and then we have to draw, okay, the curve. And then the next step is you have to determine the maximum dry density and optimum water content. Okay, here is the maximum dry density, and here this one is optimum moisture content. For example, here we have raw dry maximum 1.86 mg per meter cube, and then we have the optimum water content 30%. And next step, plot the 0%, 5%, and 10% air void line. The expression used is raw dry is equal to GS raw water over 1 plus moisture content times GS times 1 minus AV. AV is the air void, so you have to insert the value of 0% or 5% or 10%. For example, for the first one, we use 0%, so means that AV is 0%, so raw water is 1, GS is just now 2.7 if I'm not mistaken, and then GS is 2.7, and W is water content here. So for example, here water content is 10%, so means that 0.1, and then you will get 2.13, 2.04, and so on. Then you will repeat for the AV 5% here, so you insert a value of 0.05. Alright, and the other thing is same, so you get this value for air void line. Okay, so we have 1, 2, 3 air void line. Even though it's stated as air void line, so you have to draw as the curve. Alright, look at this. This is at 0%, 5%, and 10%. Alright, look at this. This one, so you have the OMC and the MDD. So here at the maximum, the air void is about 7%. Okay. Okay, determine the air void content at the maximum and dry density. So first step, maybe you can take just from the graph just now, or you can do the calculation. Raw dry is equal to this one, the equation, and then what you have to do is you insert the value of GS, raw water, WGS. W is the moisture content. Okay, the optimum water content, which is 13%. Okay, actually this one is 0.13, and the raw dry is 1.86. Okay, so you will get the AV is about 0.71 or 7.1%. Guys, ombak tu tidak besar, hanya perahu yang kecil. Jangan hanya diminta diringankan ujian, tapi pintalah kuatkan iman. Good luck.